the result about average potential, right? So I'll remind you what we discussed, and I'll prove the statement, prove the claim. Your textbook does it differently. Your textbook does it using a brute force integration and Coulomb's law. I'll do it slightly more. It's an easier trick, just works out very quickly. But as a result, you miss out on a solid integration problem. But I'll never let you guys miss out on fun. So A, you can look at Griffith's proof of the same result that I've stated, which is a calculation. But instead of me giving you that proof, I'll do a similar problem. Yeah, it's one of your homework problems, so I'll do that one as well. And the difficulty there largely is always recognizing the symmetry and then an integration. In the exam, integration is not going to be a real issue because you do it at home, you have access to an integration handbook, or you can just about Google integrals these days, and you have some time to think about your integration tricks. So what were we talking about? This is the origin of our coordinate system. And then you pick a sphere of radius r. Then the claim is the potential at 0, I mean the 0 vector, meaning the origin over here, is average of the potential on the surface of the sphere. So this is the claim. This is only true when what? Rho equals 0 inside the sphere. So there could be charges outside. Yeah? So you could have all sorts of charges, a sheet charge outside, but inside it is vacuum. Or in this area it is vacuum. Then it says if the potential here is average of the potential on the sphere. You see, this you integrate potential on the sphere and divide by the area of the sphere. That's what we mean by average. Okay, let's do a simple proof.
Isn't area of the sphere 4 pi r squared?
Ah, good catch. No, is it? 4 pi, 4 pi r squared. Thank you. 4/3 pi r cubed is the volume, but it's not 2 pi r squared. That's for sure. Thank you. So what I'm going to do, So what I'm going to do is I'm going to multiply by this and then bring it and just see if this makes sense. How did I get this? I haven't done anything. I'm just starting with this. I'll show that this is 0. But if I show that this is 0, have I proven the result? I have. I multiplied this by 4 pi r squared, but replaced 4 pi r squared with r squared sine theta d phi. So all I have to do is show that this is equal to 0. But if you're not convinced, give me some time. So this is my theta phi integral. I really should put a double integral. But this one, I'm going to write that as negative E, the electric field, dot dl from r equals 0 to some r theta phi. Then you have r squared sine theta d theta d phi. So what I've done here is I've picked any 2 points. Well, not any 2 points. This point, and it doesn't matter, this point. For some theta and phi. And then what I'm saying is, change in potential, well, isn't that the negative of the integral of the electric field? And for convenience, what I'll do, I could integrate over any path. I could integrate, right? Potential is easy to integrate over any path. I might choose to integrate over this path, actually from here to here, because it is this. But that is obviously not the path I want to choose. What path will I choose? Yeah, that's the preferred path. Okay.
One would have the 2 intervals, double intervals.
Yeah. So this is, I should put a double integral here. This is a theta integral and a phi integral. So over here, so maybe I can say this is bad notation. Okay.
So those first two are just the survivor of the dA interval.
Correct.
And then we introduce that second one to represent potential.
Correct. This is for the potential. So these two are the area integral, and this new integral that's been introduced is along my new path. Okay. And first of all, I can take this minus and change this one. So it becomes 0 to 2 pi, 0 to pi. And also, I'm going to do this ER dr then I have r squared sine theta d theta d phi. And then what am I doing? I'm going from r equals 0 to r equals big R. But then I'm going to do a slight cheat. I'm going to do 0 to pi, 0 to 2 pi, 0 to r, ER times r squared sine theta d theta phi and r squared, and then I have dr. Maybe even I can do 1 over r squared. Correct? What is this? This is nothing but E dot dA on a closed sphere, a sphere of radius r. What radius r? Well, at any point, at every point. And according to Gauss's law, what is this? Q enclosed, or Q in. But what did we say? This is equal to 0. This is equal to 0. Thereby concluding the proof. So that means this is equal to 0. But this is just a number. So this is V0 times 4 pi r squared minus the average is equal to 0. Happy? It's kind of neat, right? This seems like a pointless result, but there is a consequence of this, which is what? I'll let you copy this down, but there's a corollary. Suppose you have a region, yeah, such that rho equal to 0. Then the maximum slash minimum, I should just have said extremum, for V, the potential, this is the potential, occurs on the, is that right? Is that how you spell occurs?
Yeah.
On the boundary. You might say, well, this is, well, first of all, we'll argue this, but you might say, well, fine, you've shown one seemingly uninteresting result for another. But this is not an uninteresting result. It'll have a uniqueness theorem, the power of uniqueness theorem, soon, okay? But is the proof clear? I think I've mentioned this before. We mentioned this, but this is only true because of the previous result. That's why I'm sort of restating it. Yeah. You know, suppose I have suppose not, and if this is the V maximum, then you consider a sphere. The average must be equal to this. That means somewhere over here, there's another maximum. So it's not a maximum really, right? Unless it's constant. If it's a max, if it cannot be more than V maximum, it has to be exactly V maximum everywhere. I should say, unless V equals constant in the volume. If V equals constant, it's not a true maxima or a minima. Every point is a maxima or a minima. What's the maximum of the function f of x equals 7? 7. For what values of x? All values of x. What's the minimum for the function f of x equals 7? Yeah. Barring that, if it's a true function, then the maximum and the minimum should exist on the boundary. So look at how we're going to construct a uniqueness theorem. The uniqueness theorem, again, I won't get to that today because I want to do a brute force calculation. The uniqueness theorem is going to say, under certain conditions, if you solve the potential by guessing it, and it satisfies those conditions, you have found the potential. So if you can find a trick, use any trick that you can think of. You don't have to worry about actually using certain equations to solve. Indeed, the Laplacian must be 0. That's all that is required. We'll even do it for the case where the Laplacian is not 0 when there are charges. Okay, so hang on to this in your memory. Certainly, I don't think we'll get to it today, but we'll get to it tomorrow. Today is the rest of the day. It's kind of neat. It's an uninspired result. It's a calculation, but sometimes we just have to calculate because that's what you do in exams. Yeah. And what I'm going to do is a homework problem in Griffiths. There is satisfaction in computation. You have pinned down everything you need to. So the problem I'm going to do, and I'll also tell you why am I doing this problem. So the problem I'm going to do is problem 3.4. The reason I have to do sample problems, but I also have to do problems that are not worked out in the textbook because that would be redundant. So if you look at the proof of the previous statement that I just showed, which is potential is the average on the sphere, the proof of that is a calculation, the version Griffiths has presented. This is on page 117. And there's much to be learned by a calculation like that. Therefore, I'm just doing a similar calculation, which is problem 3.4. Problem 3.4 says the following. Suppose you have charges. Charges could be inside or outside. But I'm going to calculate the electric field produced by all the charges outside of the sphere, and I'm going to compute the average electric field on the sphere. The value I'm going to get is actually the electric field at the origin due to all the charges outside the sphere. So let's make sure you understand the problem. So let me read the actual language of the problem. It says, and make sure as I read it, it makes sense to you. Show that the average electric field over a spherical surface due to charges outside the sphere is same as the field at the center. Seems like a confusing statement, right? So let me be very specific. If I have many charges here outside the sphere. And all these charges produce what? Electric field. And then I take the average electric field produced by these charges on the surface of the sphere. The value is going to be vectorially exactly the same as the electric field produced by these charges on the center of the sphere. Okay? I can't think of an immediate great application, but it's a calculation that worth seeing. Yeah.
So at the start, you said that there could be charges inside the sphere?
Yeah, if there are, we'll ignore it.
Okay.
We're not talking about the charges due to the inside portion of the sphere. I will let you handle that on your own. Yeah. It's no different. It's one is greater than R, then you plug in less than R, it'll fix itself. Okay? I'm going to use the superposition principle, because if I can show that due to a single point charge, then it is true due to as many point charges. Yeah? And I'm going to also pick my single point charge. I can point my z-axis any way I want. So I'm going to place my point charge over here. And all I have to do is show this for a single point charge. So I am going to look at a small point over here. So the vector R is on the sphere. The vector R prime that locates the source, right? The source R prime. And R prime equals some z in the z hat direction. Yeah? My displacement vector E average on the sphere is, well, it's average. So first thing I do is 1 over 4 pi r squared divided by the area of the sphere times KQ. Let me do it this way first. R squared sine theta d theta d phi. Is that true? Yeah? But if you did this, it's slightly the longer way to do it. Which way can the electric field point? The average electric field. Look, from here to here, this is the direction of the electric field. But for every point on the sphere, there is a point on the other side wherein the electric field is tangential. And what happens? What components cancel? The x components cancel and the y components cancel too. Because if you come to this part, if there's a y component, there's the thing on the other side. So the only thing that survives is the z component. So the conclusion is E average is really equal to E average dot z hat in the z hat direction. The electric field has to be in the z hat direction. Well, what's the magnitude? It's this guy. And this guy, I will call this thing just E average without any vector notation. Yeah? And this is all there is left to calculate. Huh.
How do you say we were left with only z?
Look, see over here, there's the x component, but over here there's the equal and opposite x component. So when you integrate, this x component is going to cancel with that x component. Same argument can be applied on the y component. If you have something over here, it might have a y component this way, but on the other side, there's a y component that way. Somewhere in the middle, there will be x and y component. But on the flip side of this ball, the xy component cancels. So think about it. It's easy to say, but you have to work a little hard to convince yourself. So this is all I need. And so I'm going to cancel out the r squared, right? I'm going to bring out my kq. And then, shall I do my phi integral? 2 pi. Then I come over here. And I will write this. Tell me why I'm doing this. Why did I make it cubed? Look carefully at what I have done to the numerator. The hat has been turned into a regular vector, so I wrote it as. Good. Because the regular vector is what I have. So, r hat dot z minus z hat dot z hat. This is 1, and this is cosine theta. So then, E average equals KQ over 2 R cosine theta minus Z over, taking the magnitude. I believe we have taken this before. Yeah? Now, normally in a physics class, the teacher will say, yeah, look up the integral or do the integral. We haven't been doing too many. I'm getting some integration withdrawal symptoms here, so I'm just going to integrate, It's just good for the soul to do it. So the real problem is, of course, this cosine theta. So you do a substitution. All we have to do is compute this. So substitution, u equals cosine theta, du equals what? Minus sine theta, d at this point, also, I did actually go through the calculation, but make sure I don't make a mistake. I put the minus. Please make sure that I don't make a mistake. So minus sine theta d theta becomes du. That's why I have a minus sign. Then it is r u minus z over r squared plus, what is that, z squared minus 2r z u to the 3/2. And sine theta, theta is 0, cosine is 1, theta is pi, cosine is minus 1. Yes, Ashik. Yeah, please let me know, because otherwise we could have a train wreck later.
No, I think it will work out. No, I was thinking about something else. I think it should work out fine.
Okay, so easy for me to do. You have to write it as a different line. Look, all of you. I'm going to call this integral I. It's just a matter of calculating the integral at this point. This guy is easy to solve. We'll do it. It's this u that creates a problem. So I want to get rid of this u. So partial fractions. Who has seen partial fractions? Yeah, so again, that's the reason I'm doing it, just to revisit these things. Yeah, so I know how r is just r, so let me just look at this term. And also, bear with me, I'll show you exactly where you're doing the bearing. This is over 3/2. I'm only doing it just to the first power. Okay? I'm doing the long division. How do you do the sucker? Let me do, it should go sequentially, right? Okay, so let me do it this way first. I don't think I ever mastered long division. Look, I have this guy over here. So I'm going to do minus 1 over 2rz. When I do that, I get, what do I get? R squared plus z squared over 2rz plus u. And then when I subtract, I get a remainder of r squared plus z squared over 2rz. If you don't catch my mistake, you're on your own, okay? Therefore, I conclude that that's my remainder. The good news is, if I make a mistake at the end, I'll just write the answer down and say, well, homework. but I'm checking my steps in between. That's good. You okay with the long division? See, I have to subtract this minus this. So u minus u cancels. Then minus of this is this. This is the remainder. So quotient plus the remainder, which still has to be divided by this guy. Just a reminder of your algebra. Yeah? Oh my God. Let's do it. So I have this r minus 2rz du. I only did this. So there's a 1/2 left. Then I have r squared plus z squared over 2rz du. Oh, there's a r squared plus z squared minus 2rz u to the 3/2 minus, I cannot go beyond that line, so minus z over, nope, is that true? These two are nice. So what I could do is, because look, it's the same integral, and this is minus 1 to 1. So I can combine these two integrals. Look at what I'm going to do. First of all, I have this r over here, and this is 2z. Then I have a minus z over here. Is that true? Yeah? This is when you have to watch out, right? Always a card trick, a magician just erases something quickly. That's when the shuffling is done. Except I'm the audience member as well, because if I make a mistake, I'm in trouble. We have to hold the magic now. The trick has been done. And now look. I'm going to put the same thing back, sorry. Yeah? Z squared minus 2z squared. Squared. was it?
Single Z, over 2Z.
E.
We made a 2Z squared under 2Z.
It's not what I have in my notes. I have a cleaner version here. I just don't want to. Yeah, so my notes has a mistake. I think it is simply 2Z, correct? Are we good? Okay. Now we are ready to integrate. So this is minus 1 over 2Z. What's the integral of this? If you call this another variable, it's x to the minus 1/2. It's x to the 1/2 over 1/2, right? So let me do it this way first. R squared plus z squared minus 2rzu to the 1/2 over 1/2. But look, minus 2rz has to go over there, so I have minus 2rz. Same thing over here, plus r squared minus z squared over 2z minus 2rz. This is to the 3/2. So it's going to be r squared plus z squared minus 2rzu to the 1/2, right? Divided by 1/2, going from minus 1 to 1.
The one that's at the bottom. It's u to the negative 3/2.
Negative 3/2. So it becomes minus 1/2, right? Good. So that means this is also a good catch. So bear with me, I'm doing this over here. So first of all, let's do this. The one of the 2's cancel. The 2 negatives cancel. So what do I get? 1 over 2r z squared if this is just square root, if u is 1, its absolute value of r minus z minus r plus z. Plus r squared minus z squared over one of the 2's cancels, and once again we get 2rz 1 over r minus z minus 1 over r plus z. We have encountered this absolute value before. This time z squared, sorry. Yeah. Here, see all the errors that could be hidden has now been erased. But you know the difficulty is just paying attention. So in our case, z is greater than r. So, what were we calculating? The integral I equals 1 over 2 r z squared. Z minus r minus r plus z plus r minus, no, is that r squared? Is that r squared?
Yeah, that should be good.
Yeah. R squared minus z squared over, yeah, whatever is over has been brought 1 over z minus r plus 1 over r plus z. Let's try to simplify this. 1 over 2r z squared. I have minus r, the z's would cancel, so I have minus 2r plus r squared minus z squared times r plus z minus r over z squared minus r squared. I have no idea if we are in the right direction, guys. Minus. This and this will give me minus. And what do I have? 2z. That is not good. R plus z minus so this is minus z plus r, and this is minus 2r, so that's minus 4r over 2r z squared equals minus 2 over z squared. Yeah? Let me quickly, I think this is correct. I'm not fudging it. I'm smiling for comedic effect, really. I think this is legitimate. And then, lo and behold, I get E average equals KQ over 2 times minus 2 over Z squared. Or E average as a vector quantity, we said, was just the Z hat direction, and I would get KQ over Z squared, Z hat. And that's precisely the electric field at this point. Because if this is Q, it points this way, plus or minus, depending on the value of Q. So it's really KQ over R squared. So the point is, this and similar problems can be done. You just have to keep track of what's going on.